So let's go ahead and get started. So let's just define a couple of things. Then we're going to look at this table together, come up with some values, and then we're going to get down to the harder stuff at the bottom, which I think you guys will understand when I explain it. Okay? So first, when we talk about just experimental probability, and we define experimental probability, here's what you need to know. You can estimate the probability of an event by using data that's already been accumulated, or an experiment that's either already been done or you can do it. All right? Now, this technically has two names that you might hear. One of them I don't use very often. It's called empirical. Empirical. Empirical probability, but I use the word experimental probability. Okay? And then, of course, just like theoretical probability, here's how you find experimental probability. It's the number of favorable outcomes on top and that's going to be over the total number of outcomes on the bottom. Okay? So that's it. It's done really the same as theoretical probability. It's just you're basing your information not on theory, but you're basing your information on already accumulated data or an experiment that is done. Okay? So we got this kind of really bad bar graph here that is representing the fact that someone took a number cube and they rolled it 100 times. So instead of it being 1 out of 6 for each chances, they literally tallied up. How many times did you get a 1? How many times did you get a 2? So let's figure out how many this is going to be. I want to remind you that the number 15 is right here, like in the middle of it. 10, same. So how many of y'all think this would be? 17? I agree with that. So let's go 17. Okay, look at 2. Follow 2 over. What do you think that's at? 21? I agree. 21. We're going to check all these in a minute, and we'll be able to see. Let's follow this number 3 over. We know it's below 17, but still above 15, so let's say that's 16. Let's follow 4 over. Let's see. Looks like it's just a touch above 10. 11. Does that sound good, y'all? Let's take 5. Let's run it over. Looks like it's above 21. What do you think? 22, 23? Which one y'all want to go with? 23? 23? And then let's check this one here. Number 6. Follow it. We know it's bigger than 11.
14.
Think of 13 or 14?
14.
Huh? 13? All right, let's see if this is right. How do we know if this is right? It's supposed to be 100 rolls, right? So grab your calculator real quick and go 17 plus 21 plus 16 plus 11 plus 23 plus 13. We're at 101. All right, so out of, in my opinion, it's one of those last two.
I'm pretty sure it'd be 20.
So leave 23 alone and make 13 to 12. All right, let's make this 13 to 12. It doesn't look like it's too much above 11, but again, we're going to go with this. This matches our data, right? It's got to be 100. So as long as we all agree, that's what we're going to go with, okay? So 17, 21, 16, 11, 23, and 12 is data that they've given us, and we're going to base our probability on that data. You understand? That's experimental probability. It's basing it on data that's already been done. So based on the data, what was the probability of rolling a 3? 16 out of what? 100. 16 out of 100. So, again, I'm going to use alpha. Y equals number 1 I'm going to type 16 out of 100 in there and let it reduce it for me. 4 over 25. Or 16%. Absolutely fine with me. If you want to just say, hey, it's out of 100, so just make it a percent, that's perfectly fine. 16%. Okay? Look at number 2. Rolling a perfect square. So we're doing one fraction. But what is included in perfect squares? In our number cubes. How many of those are perfect squares?
Just 2.
1 is, right?
Yes.
And 4. Well, how many 1s were there?
17.
How many 4s were there?
11.
What's 17 plus 11?
28.
So there's 28 perfect squares out of 100. So once again, it's either 28%, if you like that, or if it's a fraction that we reduce, we need to, that's 7 over 25.
What percentage is
It'd be 28%. You see how it's over 100? It's exactly that. Because percent is out of 100. So since it's out of 100,
it? Will it be like that every time?
if it's out of 100, absolutely, yeah. Now if that's at 28 over 92, no. Okay, but if it's out of 100, absolutely. Okay, let's look at the next one. Rolling a number other than 5. Y'all remember yesterday in the notes, you learned this term called complement? Sometimes it's easier to subtract what it's not from 1 than it is to tally up all the things that it can be. For example, instead of going through here and going, okay, you got 1, 2, 3, 4, and 6 that are not, so let's add up. 17 plus 1. No, just go 1 minus, how many 5s are there?
23.
So I'm going to subtract 23 over 100 from 1. So you just go type in your calculator, 1 minus 23 over 100. What is 1 minus 23 over 100? 77. So you have 77 out of 100. 77%. Okay? Well, it would just be negative. Well, that's exactly what we did. Because remember, what is 1? As a fraction. 100 over 100. So 100 minus 23, that's what you're doing. Yeah. Yeah. Okay, next, rolling an even. Now this one, how many of them are evens? So I'm going to just add up all the 3 that are evens. So what are my ones that are even?
21, 11, and 12.
Okay, so what's 21 plus 11?
22. No,
32 plus 12. So we have 44 out of the 100. Again, if you left it as a percent, that's 44%. But if you simplified it, that's 11 out of 25. And that's how you do it, guys. You base your probability on data that's already been obtained. It's very simple, okay? It's not meant to be tricky. It's not meant to be any trickier than what you guys did yesterday. Except you just are not basing it on some theoretical idea of a number cube or a coin or whatever you might be dealing with. You're basing it on data that's already been obtained, okay? So very simple. Now, the next part of this gets a little more complicated, but I really think you guys can understand it. First thing I want you guys to do is I want you to memorize something for me with probability, okay? And you can all memorize this. In fact, you'll probably have it memorized as soon as I say it. In probability, if they use the word and, in probability, that's going to tell me that I need to multiply my probabilities. It's like yesterday. Remember how I kept saying multiple events, we multiply? If you go back and look at those problems, I guarantee you it had the word and in it. Why? Because if I'm trying to figure out the probability of this and this happening, those are multiple events. So when you see and, you're multiplying. But in probability, when you see the word or does not mean to multiply, or means to add. Okay? It's like you have a single event, but it can happen in different ways. You add those different ways. So and means multiply, or means add. Can y'all remember that? Add, or and means multiply, or means add. Okay, now let's go over here to the more complicated stuff. Mutually exclusive versus inclusive. So mutually exclusive means that there is no overlap. No overlap. None. Okay? They're completely different or separate possibilities. Completely separate possibilities. But guess what inclusive means?
They're not separate.
It means they aren't separate, that there is overlap. Okay? The data overlap. So in a way they depend on each other or they relate to each other. Okay? So mutually exclusive means they don't overlap. The information does not overlap. Okay? Inclusive means they overlap. So here's what happens with our probabilities when they're mutually exclusive versus inclusive. For mutually exclusive, when there's no overlap, and you want to find the probability of A or B, you simply take the probability of A and you add the probability of B. That's it. Okay? That's what you do with mutually exclusive. But when the values overlap, when they overlap, there's inclusive, you're going to take the probability of A, you're going to add the probability of B, just like in the last problem, but you're going to subtract the probability of B given A. So if they're mutually exclusive, you just add, but in inclusive, you're going to add and then subtract. And I'm going to explain why in just a minute, okay? This really is one of those situations where it is very helpful to have examples.
Does it matter if the B or the A goes first?
Yeah, kind of, because honestly, no, I guess it really doesn't. No, it really doesn't. I guess it would. No, not in this case it wouldn't. Okay, so here's how this works. Are y'all ready? Look at number 5. See, it says each student casts one vote for a senior class president. Of the students, 25% voted for Hunt, 20% voted for Klein, and 55% voted for Vila. A student from a senior class is selected at random. One student. But they want to know what's the probability that a student voted for Klein or Vila. So again, that or tells me I'm doing what with my fractions? I'm adding them. Now here's my question. Are these mutually exclusive or are they inclusive? Let me ask that one more time. Is there a chance that this data could overlap or no chance that it would overlap? So can you vote for Klein? How many people voted for Klein?
20%.
Now they didn't use a fraction, so we're going to use 20%. You could do 20 over 100. How many people voted for Vila? 55%. Now here's my last question. Did anybody vote for Klein and Vila?
No.
See, they're not overlapping. You either voted for Klein or Vila or Hunt. There was no chance that you voted for both. These are mutually exclusive. That means all you do is you add up these probabilities. Since they're in percentages, I just leave them percentages. What is 20% plus 55%? So there's a 75% chance of voting for Klein or Vila. You understand that? Now here's the opposite side of this. I want you to go over here to number 6. I talked to you guys a little bit about a deck of cards yesterday, remember? Explain some things. Most of you guys maybe already knew it, but there's some things that are important, okay? 4 suits, 13 cards in each suit. Face cards include Jack, King, Queens. Some basic things. Well, here's the question that's asked on this problem. A single card, is chosen from a standard deck of 52. Find the probability of drawing a red card or a face card. So that or tells me I'm doing what? I'm adding. Okay, so let's focus just on the first one. How many are face cards? I'm sorry, so about the first one was how many are red?
6.
Nuh-uh. How many are red? 26, right? 26 are red out of 52. Half of them, right? 13 diamonds, 13 hearts are red. Okay, second question. How many cards are face cards? 12, right? Because there's a jack, king, and queen, and I always say those backwards, of diamonds, hearts, clubs, and spades. 4 suits, 3 face cards each. 3 times 4 is 12. There's 12 total face cards. Now, here's my question. Do we have red cards, that was my first category, that are also face cards?
Yeah.
Yes. You see, there's overlap. There are certain cards that fit in both categories. When there are cards, or whatever your thing may be dealing with, that fit in both categories, you have to subtract that overlap at the end. That's the concept of inclusive. Are y'all following? So think about this. How many cards are red and face? 6. So we have to subtract 6 out at the end because they got double counted. And we can't double count stuff without making amends for it. So since the red cards that were also face cards got double counted in both categories, we subtract those red face cards out. Y'all follow? That's the difference between mutually exclusive and inclusive. You follow? All right, so type all that in your calculator, please. You're going to use alpha y equals hopefully, and you're going to let it do all the work for you. You should have gotten 8 out of 13. If you didn't, type it in again, but you should have gotten 8 out of 13. All right, now I'm going to skip number 7 out like it, and let's go to number 8. Everybody ready for 8? Okay, listen to this one. A bag contains 25 marbles. There are 10 that are black, 13 that are red, and 2 that are blue. A single marble is chosen. What is the probability of getting red or blue? So we know we're adding. So let's start with the first one. What's the probability of getting red?
13.
13 out of 25 total marbles. What's the probability of getting a blue one?
2 out of 25.
2 out of 25. Now listen, in this description, are there any that are red and blue?
No.
So these are mutually exclusive. There are no overlap. Therefore, do we need to subtract anything out?
No.
Nothing. So all we do is add 13 over 25 and 2 over 25. And that will reduce down to, actually should be 3. Yeah, 3 over 5. So, mutually exclusive versus inclusive. Y'all cool with it? Okay, let's finish up. This is a pretty hard one. It's got one hard thing to find, and then once you find it, it's pretty easy, okay? 5 years after 650 high school seniors graduated, 400 had a college degree, and 310 were married. Half the students with a college degree were married. Okay, ready? First, how many had a college degree? 400. So listen to this, guys. If 400 had a college degree, how many didn't?
200.
How'd you go on 250? Exactly. There were 650 people. So 650 minus 400 is 250. That's how many people did not have a college degree. Okay, next. How many people were married?
310.
310. So how many were not married? 340. Again, how'd that 340 come about?
Subtracted it from the original.
Right, there were 650 people. If 310 are married, that's 340 then or not. Now, last, it says half of those with a college degree were married. How many had a college degree? 400. So what's half of that? So how many were college degree and not married? Also 200, right? 400 minus 200. Okay, now this is the hardest one to find. This is the one people struggle with. How many were no college degree but married? Anybody got an idea? No college degree.
I was gonna say
310
one.
minus.
Exactly. It's 310 minus 100. Let me explain. No college degree and married. Well, remember, how many were college degree and married? 200. How many were married? So if there's 310 married and 200 of them are in college, 110 are not. Does that make sense? That's the hardest one to find. The other one is not quite as hard because how many people are no college? 250. How many are no college and married? 110. So how many are no college not married? 140. So there's all my data. Sometimes it's really nice to find all this data before you start answering the next questions, okay? Let me explain. Look at this one. What is the probability that a student has a college degree or, adding, right, or is married? Okay, so first, how many have a college degree? 400 out of 650, right? What's the second category? Married. How many were married? 310 out of 650. Now listen, here's the thing. Is that mutually exclusive or is that absolutely inclusive? Are there people who are college and married?
Yes, it's gonna.
Then those have to be subtracted. How many are college and married? So we're going to take 400 over 650, and we're going to add that to 310 over 650, but then we have to subtract those that overlap, which is 200 over 650. So you're going to use the alpha y equal, hopefully, and when you do, you reduce this down to 51 over 65. That's the idea of inclusive. Y'all follow? So look at this next category, number 11. What's the probability a student has a college degree or is not married? Okay, so pause. Or, adding, right? What's the first category?
College degree,
How many have a college degree?
400.
So 400 out of 650. What's the second category?
Not married,
How many are not married?
340.
So 340 out of 650. But are there some that are college and not married?
Yes.
How many?
Um,
So we subtract 200. We subtract those that overlap. So it's 400 over 650 plus 340 over 650 minus 200 over 650. So tally that all up. You should get 54 over 65. Okay? Last one. What's the probability a student does not have a college degree or is married? So we're adding, because they say or. So let's start with the first one. How many do not have a college degree?
200. No,
250.
250.
250. Next category, how many are married?
310.
310 out of 650. But are there people that are not college and married?
Yes.
Yes,
How many?
110.
110 is how many we subtract. Do y'all understand this concept of mutually exclusive versus inclusive?
It's actually
Took me a
pretty
minute.
Yeah, it is, right? So 250 out of 650 plus 310 over 650 minus 110 over 650 reduces down to 9 out of 13. So hopefully, the more practice you guys were getting with this, you were starting to kind of catch on a little better. So your homework on this worksheet is the front side only. That's 1 through 10. 10 problems. Y'all do have a chart, one chart like this that you have to kind of follow. We'll see how you do on that. Pretty good question, honestly. So front side only. Don't worry about the back. Just numbers 1 through 10 is your homework, okay? Again, if you didn't finish last night's homework, please finish it up, put it in the folder.